Hello and welcome back. Today we're going to talk about Chapter 2 Incline, and it starts with a review of some of the skills we looked at in Chapter 1, line drawings, formal charges, lone pairs, and then we're going to move into the topic of resonance and get into that in a lot more detail than you've probably seen in general chemistry. So I have here the lecture notes for Chapter 2, and one of the things that the textbook starts with is talking about condensed formulas. So if we think about this organic molecule where we have it all totally drawn out, you can see every single carbon, every hydrogen, all the bonds. You can start to condense some of those things so that the CH3 group, instead of drawing out all those hydrogens, you could just draw it as a CH3. But then you can, in the CH2s, you can condense down, but then you can condense it even further to maybe group the CH3s together. We have three CH2 groups, so we can group all those together. This CO2H group we can condense as well. So there's varied levels of condensing that can go on, but the condensed formula, when it's shown, does communicate some information about how the atoms are put together, how they're connected. So you should be able to go from a condensed structure to a complete structure. And we'll get some practice with that today. Also, line drawings, we had some experience with that in Chapter 1 on recognizing, and interpreting line drawings. So we'll get a little more practice with that. And then also in Chapter 2, you'll see some a skill builder where it asks you to draw a line drawing given a condensed structure or some other representation of the molecule. Okay, so just a reminder here, what does a line drawing represent? Any endpoint of a line and any intersections of lines represent carbon atoms, and then we just leave off any hydrogens that are attached to carbons. So if we take a look at this this carbon chain, this represents a carbon atom. These all represent carbon atoms, 1, 2, 3, and a triple bond looks a little strange in a line drawing, but what it's representing is a triple bond between two carbon atoms. So that's those are intersections of lines as well. And here's one more carbon. And then how do we know how many hydrogens there are attached to each position? Well, remember carbon, any neutral carbon must have 4 bonds. So we can just see how many hydrogens need to be added to come up with a total of 4. So this carbon has 3 bonds shown to other atoms, and so there must be 1 hydrogen at that position. Okay, the triple bond has 4 bonds already. The other side of the triple bond, that carbon has 4 bonds already. The next carbon over also has 4 bonds. So the only other places we can look for hydrogen atoms are at these endpoints. And at any endpoint where that carbon is attached to the rest of the carbon chain just by 1 bond, that must be a CH3 at each of these positions. So these are each CH3 groups. So overall, we could determine the formula of this structure. Just a little reminder there of how we might do that. So we have 1, 2, 3, 4, 5, 6, 7 carbon atoms. We have 7 carbon atoms. Our hydrogens, we have 3, 6, 9, 10. We have 10 hydrogen atoms. And then we have 2 chlorine atoms. So interpreting our line drawing. So let's look at a few more examples here. These are some more interesting organic molecules. Too easy to find those. Let's see, one of these compounds makes life sweet. Another one is another example of a sex pheromone, this time for a housefly. One we might use if we're grilling some burgers. And another one is a carcinogen. So so which is which here? Let's first interpret our line drawings and then we'll match them up. So again, this 6-membered ring, this hexagon, represents 6 carbon atoms in a ring, and then this one has 1 hydrogen attached at each position to get to a total of 4. That compound is benzene. And benzene is a liquid. It used to be used as a solvent very commonly until it was discovered that it was carcinogenic. What does it mean to be a carcinogen? it means it can cause cancer. It can cause cancer. So benzene is a known carcinogen. How about this next structure? This has 1, 2, 3 carbons. So how would we expand? What would the condensed structure look like for this? That first carbon has how many hydrogens? It is a CH3. The middle carbon is a CH2, and the end carbon is a CH3. So that line drawing represents a 3-carbon chain that is known as propane. And where might you find propane? You might find propane in a barbecue grill. So propane and propane accessories, or where you can find some more organic chemistry. So that's another fuel that's used. This one is used a lot in very often in portable barbecues. How about the next one? Let's answer the question first. How many carbon atoms? Maybe you can pause the video, see if you can count them up, see if you come up with the same number I do. We have in the ring here, we have 1, 2, 3, 4, 5, and then there's 6 carbons on the left-hand ring. And on the other side, we have 1, 2, 3, 4, 5, 6. We have another 6 carbons there as well. So there's 12 carbon atoms, 12 carbon atoms. And this is the structure of sucrose. That is table sugar. That's table sugar. So that is something that makes life sweet. Makes life very sweet. All right. I just counted 2, 4, 6, 2, 4, 6. Okay. And our last one, how many carbon atoms are in this one? This is, let's see if I can use a highlighter. Let's count some of these. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 23. So it looks like there's 23 carbon atoms. Again, imagine having to draw out this structure. Every single carbon and hydrogen are CH3, CH2, CH2, CH2. That line drawing just lets us draw it very, very quickly. So there's 23 carbon chain with a double bond, a carbon-carbon double bond at this position with the cis stereochemistry where both those carbon groups are on the same side of the double bond. This is the pheromone that the common housefly uses as a sex attractant. So that is that's another interesting organic molecule. So just some practice with line drawings. Make sure you can interact with those. You can you know, provide a line drawing or interpret a line drawing. We're going to be using them extensively throughout the whole year of organic chemistry. Okay, let's look at one more example to try. This shown below is the structure of nicotine. This is a stimulant that's in cigarettes and electronic cigarettes as well. That is as addictive as heroin. So that is, you know, it's a stimulant, but it's also something that can very easily get you addicted to those products, to vaping or to smoking. So let's take a look at this. Can you fill in any missing hydrogen atoms? And then again, what's the molecular formula of nicotine? So again, if you want to pause the video and try this on your own, that'd be a great exercise, but I will work through it myself. So this bottom carbon I already drew out as a CH3, so there's no missing hydrogens here, but each of these carbons in the chain has only 2 bonds. Those must all be CH2s. Those must all be CH2s. And how about this carbon? That carbon has only 3 bonds, so there's also a hydrogen. Notice the stereochemistry here, this the 3-dimensional shape. This is a tetrahedral carbon. The 6-membered ring is pointing away from us, so the hydrogen that is missing must be a wedge sticking out towards us. We can show that tetrahedral shape at this carbon. This carbon atom is sp3 hybridized. So that would be a way that you can draw where that hydrogen is. And then how about on the ring? This first carbon already has 4 bonds, but the next one only has 3 bonds. So at each of the carbons on the ring, there's only 3 bonds. And so there is a hydrogen at each of those positions. And then how about nitrogen? Nitrogen has 3 bonds, that makes it neutral. And of course, if there was a hydrogen on that nitrogen, we would have to show it. The only hydrogens that are missing in a line drawing are those that are attached to carbon. So how about the formula? How many carbons do we have? We have 1, 2, 3, 4, 5 over on the right-hand side, and 1, 2, 3, 4, 5 over on the left-hand side. So it's C10. And then when we add up our hydrogens, we get 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. C10H14 and 2 nitrogens, 1 in each ring. So line drawings, some interesting molecular skill builders 1 and 2. Skill builders 1 and 2 give us some practice in working with condensed formulas and with line drawings as well. All right, so how about the next ones? Can we draw all the atoms out from the expanded structures, so showing the connectivity and so on, and then provide those same drawings as same compounds as line drawings instead. So so how can we do that? We can kind of think about this carbon. We could start with this carbon here. Okay, what does that carbon have on it? It has a hydrogen, and then it has 2 of these 2 carbon groups. So it has 2 of these 2 carbon groups here, and we can draw out all of our hydrogens. This is a CH2, and this is a CH3. This is a CH2. This is a CH3. Now, again, it doesn't matter where I'm drawing this. I'm just showing the connectivity. So it doesn't matter if you chose to draw it up or down or to the left or to the right. That's all good. Okay, now we have this CO2 group. So that's a carbon and an oxygen and an oxygen. Remember, we want to avoid drawing a peroxide group, a peroxy group with 2 oxygens directly bound to one another. And the convention for a condensed formula also is that immediately after the carbon, you're going to list all the things that are attached to it. So CH2, these 2 hydrogens. So CO2, that means there's 2 oxygens. And so I know I need a double bond here to connect those so that the carbon has 4 bonds and the oxygen has 2 bonds. And then what do we have next? We have a CH2 and then a CH3. So that's how we can get that connectivity of each of our atoms, and that would be the totally drawn out structure. So what would that line drawing look like? So the line drawing, we get rid of all the carbon atoms. We don't draw any carbon atoms. So that CO double bond is represented like this. And then we have an oxygen and then just 2 carbons, 1, 2, right? You can kind of think about 1, 2 to make sure you still have those 2 carbons. And then on the other side, that bolded carbon is attached to the CO double bond, and then we have a 2 carbon chain and another 2 carbon chain. Okay, now the bond angles don't have to be beautiful in a line drawing, but typically we draw everything kind of at a 120-degree bond angle so that they're not overlapping with each other, and they're kind of representing what the 3-dimensional structure looks like to some extent. All right, how about our next one? You can, again, kind of start anywhere you want. Let's start at this left-hand side. We have an NH2, and then we have a CH2. And then the next carbon has a CH and a Br. So that hydrogen and bromine are both attached to that carbon. Remember, bromine likes to have just 1 bond, just like hydrogen. And so those both must be attached to the carbon. And then what about the next carbon? The next carbon has 2 CH3 groups attached, CH3 and CH3. And then we have a CH with a double bond. And then we have 2 of these groups, CH2OH groups, attached to that carbon, right? So we have a CH2OH and a CH2OH. Again, it doesn't matter which direction you put those 2 hydrogens on the CH2. So that is the expanded structure from the condensed structure. What would the line drawing look like? Again, we can kind of start any direction you want, doesn't really matter. But we have an NH2 group, and then we have just a regular CH2. So that's just going to be a bend in a line. We're going to draw kind of our zigzag drawing. And then we have another carbon. This time it has a bromine attached. So we can point that up. The next carbon over has two CH3 groups. So we can point those down here as line drawings. That represents two CH3s. And then the next carbon is a double bond to the next carbon over. And then that last carbon of the double bond has, again, a CH2OH and a CH2OH. So that's one carbon, and then an OH, and then another carbon and an OH. So as you get practice with your line drawings, you're going to see every time we have a bend like that, just a regular bend in the line, that represents a CH2 group, right? And the end point of any line always represents a CH3 group. And notice too, when I kind of draw my zigzag, any attachments, from a zigzag up, I'm going to draw up here. Any attachments to a zigzag down, I'm going to draw down here. Those are kind of the best looking line drawings. That's kind of the habits we want to get into. Fantastic. All right, let's get a little more practice drawing lone pairs and formal charges, which we've already done, looking at Lewis structures in chapter 1, but there's a few more skill builders, 3 and 4 in chapter 2 that work on finding formal charges. So can we find any missing formal charges on the following structures? I've shown all the lone pairs that are present and what, if any, charges are there given these structures. Now, again, if you want to pause the video and try this on your own, that would be a great exercise. But otherwise, I will go through here. Now, remember, carbon atoms, anytime I see a carbon with 4 bonds, I know it's neutral because that's its typical bonding pattern. So, these carbons here don't have any charge. But this carbon, something I need to check that out because that's not the typical bonding pattern. So how do I calculate my formal charge? I count just 1 for each bond, 1, 2, 3, and then I count both electrons of the lone pair. So this carbon actually has 5 electrons around it that it kind of owns. But remember, carbon only wants 4 because that's its valence. So if I have 1 extra electron, that means I have a negative charge because, of course, electrons are negatively charged. Okay, this carbon also I want to check out because it doesn't have the usual 4 bonds. So how do I calculate its formal charge? Same thing, 1, 2, 3 for the 3 bonds. This carbon has only 3, but it wants 4. So in the case where I'm missing an electron, that's where I would assign a +1 formal charge. So again, just put a plus and a circle around it. An oxygen with 2 bonds, 2 lone pairs is a neutral oxygen. We could double check that. 1, 2, 3, 4, 5, 6. So yes, that in fact matches the valence of oxygen, which wanted 6, and it has 6. But this top one I need to check out. So we have 1, 2, 3, 4, 5, 6, 7. This oxygen has 7. So once again, an extra electron means that that would be an O-. So this Lewis structure, notice, has a net charge. Overall, this is an ion. It has a negative charge, -1 charge. And the Lewis structure I've drawn actually has 3 formal charges within it. All right, how about the other side? A nitrogen with 3 bonds and a lone pair is neutral because it has 1, 2, 3, 4, 5, which matches the nitrogen valence of 5. So this nitrogen is neutral, this nitrogen is neutral, 3 bonds and a lone pair, but this nitrogen we need to check out. So it has 1 bond here, right? So that's 1, 2, 3, 4, 5, 6. This nitrogen has 6 electrons, which means it has an extra electron that is an N-. That is an N-. How about the carbon atoms? Do all the carbon atoms have 4 bonds? Exactly 4 bonds? Yes, in fact, they do. Every one of these carbons, again, even in the partially condensed formula or structure, you should be able to interpret that. So that's the only formal charge in that second structure. All right, now can we go the other direction? What if I show you all the charges? Can you determine where there are missing lone pairs? So if we look at our next one, So we have, how about a neutral oxygen? A neutral oxygen that has lone pairs, right? That has 2 lone pairs to match its 2 bonds. That comes up to a neutral oxygen. And so how do I get to a oxygen with a negative charge? Now I have 1 bond and 3 lone pairs. So this is still has a filled octet, notice, and O- still has a filled octet. It has 8 total electrons. But now when we count, we have 1, 2, 3, 4, 5, 6, 7. That's what the goal is. We need to have 7 instead of 6. That's how I know I have a negative charge. How about this nitrogen? Any lone pairs on this nitrogen? It's a positively charged nitrogen. And right now we have 4 bonds, right? These are hydrogen atoms here. So we have 4 bonds, 1, 2, 3, 4. So actually that's a complete nitrogen filled octet. And with only 4 as its electron count, that's where the positive charge comes from. So no lone pairs there. Anywhere else you might expect lone pairs? Let's remember a little bit of our periodic table. Where is sulfur in the periodic table? Right here underneath oxygen. So just like a neutral oxygen has 2 bonds, 2 lone pairs, a neutral sulfur also has 2 bonds, 2 lone pairs. So that we would add lone pairs there. So we can check our math. 1, 2, 3, 4, 5, 6. And sulfur, just like oxygen, has 6 valence electrons because it's in group 6. All right. How about this one? We have a whole chemical reaction here. This is a proton transfer reaction, an acid-base reaction. We're going to study those in the next chapter, chapter 3. Can you fill in any of the missing lone pairs in each of these 4 structures? Any lone pairs throughout? Again, try pausing the video. Try pausing the video, and let's see if we can do it together when you're ready. So H2O, water. Yes, that oxygen has 2 lone pairs because it's a neutral oxygen. HCl, any halogen like chloride, if it's attached, if it has that 1 bond, then it also has 3 lone pairs. That gives it an octet. And also let's check out its formal charge. 1, 2, 3, 4, 5, 6, 7. There it is, 7 to match its valence. So that would be a neutral chlorine atom. Okay, but what about hydronium, H3O plus? Any lone pairs there? How do I get a positive charge on oxygen? I know oxygen wants 6, so a positive charge means it only has 5 electrons around it for its formal charge count, its electron count. So we got 1, 2, 3, and so what does it need? It must have a lone pair. It must have a lone pair as well, and now it has a total of 1, 2, 3, 4, 5. That gives it an O plus. And finally, how do I get a Cl minus instead of 7 electrons around it? Like this chlorine atom, this chlorine must now have 8 electrons around it. That's what gives it a negative charge. So if we add in 4 lone pairs, then that would work out just right. Fantastic. All right, so skill builders 3 and 4, adding in lone pairs and adding in formal charges, that is all good practice. And then one last thing, just looking at all these structures here, can you identify any places where we have atoms with missing octets? That's going to be pretty rare. Usually our atoms want to have filled octets, filled valence shells, but are there any positions you can find where there's a missing octet? Again, try pausing the video, see if you can find them, and then we'll look together. All right, it turns out that every single atom in every one of these Lewis structures that are shown on the screen right now have filled octets except for one. There's only one position where we are missing an octet. The missing octet is right here. That's the only carbon. When we look at how many total electrons around it, we only have 2, 4, 6 electrons. 6 electrons missing octet. Every other atom, of course, hydrogen just having 1 bond and 2 electrons. Every other atom has a total of 8 complete electrons around it. And so this is going to be true. This is, remember, I use this term. It's called a carbocation. It's called a carbocation. When you have a carbon with a positive charge, it's always going to have just 3 bonds around it, and it's always going to be missing an octet. We are going to be seeing lots of carbocations around, but it's in general, it's the only type of atom we're going to be seeing that's missing an octet that we're going to be seeing pretty regularly. All right, so that wraps it up for now. This is a good stopping point. What we'll move into next is the concept of resonance, and you'll see that in the next video. All right, have a good one.